engineer secure solutions to reduce or eliminate the consequence of those most catastrophic attacks.
Welcome, listeners, to the Industrial Security Podcast. My name is Nate Nelson. I'm here as usual with Andrew Ginter, the Vice President of Industrial Security at Waterfall Security Solutions. He's going to introduce the subject and the guest of today's show. Andrew, how are you?
I'm very well. Thank you, Nate. Our guest today is Jodi Jensen. I've worked with Jodi on and off over the course of many years. She's currently the president and owner of Secure SCADA Solutions. And our topic is we're going to look at Jodi's experience using the consequence-driven cyber-informed engineering methodology, CCE. How it worked for her and what she learned from it.
Then without further ado, here's you and Jodi.
Hello, Jodi, and thank you for joining us. Before we get started, can you tell us a bit about yourself and about the good work that you're doing at Secure SCADA Solutions?
Hi, Andrew. Thank you so much for the opportunity to speak to your listeners today. It's been such a pleasure getting to know you over these last few years, and I appreciate your insights, so this is quite an honor. As far as my background, I have 20 plus years being responsible for control center SCADA at Western Area Power Administration, which I may call WAPA at times during this podcast. I had the benefit of working to support operations of the power grid across multiple states. And this started with a job in programming SCADA. And what's interesting about this is that it was very unusual that the managers of this particular organization at that time had a homegrown SCADA. So I was actually doing programming as a SCADA vendor would. And so I had that type of background. I wrote nearly all the interfaces from SCADA to external systems like historians and external entities and so on. ICCP is one of the capabilities that I had written applications for. And because of that responsibility for all systems, I ultimately became the person responsible for audits. There are two types of audits that we would have to, I want to say, endure. And one of those is NERC SIP audits. I would have been the first person to implement solutions to pass and secure the systems in a SIP audit. And as well as we were federal, so I was also responsible for the FISMA requirements, which are all based on NIST. And so a lot of responsibility to ensure that the solutions we implemented not only operated the power grid, but also kept the critical infrastructure secure. And then after that experience in the last few years of my time at WAPA, I was the senior SCADA advisor for all of WAPA's control centers. And I focused on security because that became a passion of mine. I worked with the national labs like Pacific Northwest National Lab and Idaho National Labs. I worked with NERC I was on their SIP 12 drafting team, and I was working with guidance for operational requirements around data exchange. I also have a lot of industry engagement, worked with EPRI, the North American Transmission Forum, NERC organizations like WAC and MRO, which are reliability organizations. And so I'm bringing that kind of background to provide SCADA services. As a senior SCADA advisor, I was doing so. And now that I'm retired from WAPA, I am bringing my background to a broader audience in my new company called Secure SCADA Solutions.
Before we get into industrial security, we've never had somebody on from a transmission control center. So, can we use the opportunity here to sort of tap your experience? What is a transmission control center? How does it work physically? How does it work automation wise? Can you give us some background here?
Sure. Transmission control centers are required to monitor and control the transmission grid. And so all transmission facilities are being monitored and controlled at a control center. And one of the other functions that is performed at these control centers is often, and to some degree, generation control as well. And so in the transmission control center that I was responsible for the SCADA systems for, we were doing monitoring and control of transmission facilities across 7,000 miles of transmission. And we also controlled generation from the federal facilities. We balanced generation with load. And that means when you're responsible for operating the transmission system, you also have to ensure that energy is flowing to meet the demands and keep the lights on. And so there's a balancing function that is performed by a lot of the control centers. And that balancing function is to ensure that we're every 2 seconds, we're measuring what generation is needed for the next 2 seconds. And that balancing function has to take into account outages of transmission and all kinds of different things that may happen. These transmission control centers have dispatchers and operators that are observing the 2-second data that's coming from substations, and they're making split-second decisions to address things like a high voltage condition or an outage that's planned. They have to manage planned outages to ensure that the maintenance workers can work on lines without being unaware of something that's energized. They have to do unplanned outage management in order to reroute power to ensure the electricity stays on. So at the foundation of all this capability in transmission control centers, there's the SCADA system that enables it all. It enables the monitoring and control. It enables the switching that happens to de-energize and energize substation facility devices. It's also taking generation on and offline in some cases, or adjusting generation to adapt so that the load is being met by the right amount of generation. And so this is kind of a high view, but one thing that I want to note is that this is changing a lot with the advancement of markets. And so now that there's markets where generation owners can bid their generation into a market, these markets are using the SCADA systems at these transmission control centers to receive the monitoring information they need to run the market, as well as the control that they may do through the control center to adjust generation. So it's changing. And there's also a reliability coordination piece where data exchange in and out of these SCADA systems is critical.
So Nate, I always ask our guests a question like this because, I like to understand the physical process we're working with. And we're going to be talking about, the CCE in a minute. And one of the big drivers of CCE decision-making is physical consequences of cyber compromise. And so you have to understand the physical process in order to be able to understand these consequences. And Jodi talked a lot about details. Let me add just a little bit for the non-engineers in the crowd, sort of the very basics of power transmission. We're talking about the transmission lines, the big high voltage transmission lines you see running across the landscape. These things connect the generators to the cities, to the loads, to where the power is produced, to where the power is consumed. It's done at high voltage because you want to lose as little power as you can as you transmit it across, sometimes thousands of miles. and you lose much less at a high voltage than a low voltage. And so the substations she's talking about are the main thing in a substation is what's called a transformer. And the transformers change low voltage that's coming out of the generators into the high voltage to go through the lines. And then on the other end, back into the low voltage to go into the cities, because you don't want to fry people in their homes. And what we're talking about here, what Jodi's main experience is with a transmission control center. And to an extent, these control centers control the entire grid. They tell the generators how much power to produce second by second to match how much power the grid needs second by second. And they also work with real-time markets. It's like a stock market where power is sold second by second, bought and sold, so that the grid has access to the cheapest, the most efficient power as the minutes go by. So it's a very real time thing. And to her point earlier, we're talking high voltage, we're talking safety critical. If you mess with the transmission line that somebody's working on, this is a very serious problem. So these are the kinds of consequences we're going to build into using this background. Our topic today is CCE, the consequence-driven cyber-informed engineering methodology. Can we start? I mean, we're going to talk about your experience using CCE, for a risk assessment. Can we start with CCE? What is CCE? What are we talking about here? I mean, we've had entire episodes on CCE, but if we could hear it from your mouth in terms of sort of your view of the elephant, what is CCE to you?
Well, I really like the way you asked that question, because I really don't want to give a textbook definition. I'd much rather describe it the way I see it, having been through and having led a CCE engagement for WAPA. I am not going to provide any information about the WAPA CCE engagement, because obviously this is sensitive information. But I did have information that I wanted to share that is kind of bigger and broader, because I have that industry outreach role. I recognize that, some takeaways that might help industry. But CCE, in my viewpoint, is focused on identifying high consequence impacts that could result from a cyber attack. So, and really what you want to be able to do with that, once these consequences are fully understood and the dependencies are fully understood, then you engineer out risk. You engineer secure solutions to reduce or eliminate the consequence of those most catastrophic attacks. And that's how I see it. Now, one thing to add to that is there's an assumption throughout the CCE engagement process that a well-resourced nation-state threat actor would actually be able to attack you and cause that high consequence event, but for some mitigations that you may want to put in place. And so what makes it different from the protections and controls that we're always talking about and implementing, this assumes that your attacker is going to get in, and you're really focused with CCE on how to reduce the consequence should that attack occur.
Okay, so that's what is CCE. I mean, how did you get involved in the process of using CCE?
Because WAPA is a DOE utility and we operate critical infrastructure, and Idaho National Labs is a DOE organization as well, I think it only made sense that DOE would request WAPA to undergo a CCE engagement. And I had the good fortune of being asked to lead the effort. And I also was in that process, then built my team of professionals to be able to complete that high consequence identification process. And, really, I did want to mention that long before I had the opportunity to work on a CCE engagement with the labs, I believed in the principles, and I strongly believe in the principles to this day. One of the things that comes from my programming background is I understand the vulnerabilities that are going to be in the code. And so when you develop cyber solutions to protect cyber solutions, and then those cyber solutions need protection, you get kind of an infinitely recursive problem, and it requires more than just cyber protections. You have to start focusing on resilience. And so I'm a big believer in this. We have to identify ways to reduce high consequences or eliminate high consequences. And I've found too that architectural solutions that facilitate recovery from any type of failure. And keep in mind that the folks that manage these systems have already had to deal with all different types of failures, not necessarily cyber attack failures. And so using that knowledge to identify ways to architect and facilitate recovery can really be beneficial. And all of this goes to the principles of CCE that are about reducing consequences of an attack.
So Jodi's been referencing consequences as it pertains to CCE, but Andrew, what kinds of consequences are we actually talking about here?
Jodi, is naturally reluctant to talk about anything specific coming out of the engagement at WAPA because it's confidential. But let me just say generally, if we're talking a transmission grid, there tend to be at least three kinds of consequences that are sort of top of mind for everyone. This is just sort of instinct in the space. Everyone knows this. Of course, people outside the space like me had to learn it. So the three we're talking about are cascading failures. This is where, let's say there's some kind of failure that occurs on a leg of a transmission grid, on, the connection between two substations. It might be a mechanical failure, a tree falling on the line. It might be a cyber failure, an attack that takes down the controls. And so the line is de-energized, has no power flowing through it. But when you lose a line like that, what happens is now the electricity naturally, physically, this is the physics of electricity, it starts automatically flowing through other parts of the grid and may overload another leg of the grid. And the computers watching that say, oh no, it's overloaded, and they stop the flow of power through that leg of the grid, which automatically transfers the power to other legs, which then overload, which trip. And you wind up with what's called a cascading failure, where basically a large chunk of the grid just drops because it was sort of running on the edge of what was possible, and you lost something critical and the whole thing goes down. This is what happened in the American Northeast in 2003. The other kinds of failures that people is always top of mind for the engineers are equipment failures. So if, let's say, you overload a leg of the grid and you don't shut down that leg of the grid because the protection system, the computers that protect from equipment damage, have been sabotaged or are misconfigured or something, you risk burning out high voltage transformers because they're overloaded. Here's the problem: when that happens, it is going to take months to build another transformer from scratch to replace the burned out transformers. And now you have long-term outages we're talking about. And the same thing with rotating equipment in the generators. You've got, a steam turbine or a gas turbine, 300 tons of rotating metal. And if you mess with that in just the wrong way and you damage the generator or the turbine, now, again, you've got a months long or, as much as a year long outage for that generator. And you've got sort of it's not permanent, but it feels, for a year, it feels like a permanent impairment to the grid. So cascading outages, damage to transformers, damage to generators. These are sort of the three consequences that are front of mind for everybody in the transmission grid: engineers, cyber people, everybody.
Andrew, I've got so little experience with how the power grid works, so I just have some sort of clarification questions about that answer you just gave. Number one, you mentioned a scenario where a transformer is just sort of taken down, destroyed, out of commission, and you need months and months to sort of get back to a place where you can, replace it. Even if these are large and big and bulky and expensive machines, why isn't it that we can keep some in inventory for that worst case scenario?
That's a very good question. That's a question that was asked after the 2003 outage. There's a couple of answers. One of them is that these high voltage transformers, they're designed to be extremely efficient because there's thousands of them in the grid. And every, watt of power that they consume in terms of inefficiency, in terms of heating up instead of transforming voltage, is power wasted. And so they're designed to be extremely efficient. They're built by hand to be exactly what's needed for a particular substation, because the substation has transmission lines, physical cables coming into it, going out of it, and these cables have specific electrical characteristics. They can only carry so much voltage, they can only carry so much current, and so the transformer is designed exactly for what's needed there so that it can be as efficient as possible. As far as I understand, these things are still made largely by hand. This is a craft. There's people who specialize in hand wrapping insulation around the cables inside the transformers. This is why they're so efficient. This is why they take so long to produce, because they're done by hand.
I guess I understand that, although couldn't we just make sort of, I don't know, for lack of a better word, like generic transformers that can apply to different substations? And maybe they're not that efficient, maybe they're not that customized to the particular application, but they'll keep the power grid going.
And the short answer is yes. And in my understanding, this is something that was done after the 2003 outage. Now, it was done in secret. As far as I know, the information about the inventory, there was an inventory that I believe it was announced that, North America, the American Department of Energy, somebody was investing in, and but it was classified. The details of it were classified, how efficient they were, how many of these devices are in inventory. But there is apparently an inventory now in at least the United States. I don't know about other jurisdictions. There's electric power, there's transmission systems all over the world. Do they have these kinds of protections in terms of inventory of high voltage transformers? I'm not sure they do. They're generally, you can't go and buy a high voltage transformer off the shelf. There is no commercial inventory of these, but in my understanding, there is now a strategic inventory that I don't have any details on.
And is there any good reason why this is so secretive?
I believe it's because the nation does not want, our enemies to know about how much damage they have to do before it turns into something that is long lasting. So we're talking about damage to national critical infrastructure, the same infrastructure that supplies power to military bases, supplies power to civilian infrastructure. This is why, in my understanding, it's secret.
And the other clarifying question I had is, you mentioned that 2003 blackout. I remember living through that blackout. I was actually on vacation with some family in Canada where, the problem, if I recall, began in Ohio and then spread throughout the Northeast. What I'm curious about is why we don't have some means of installing breakers that prevent a local problem from becoming a much more widespread one, so that somebody in Canada would be affected by something that's happening in Ohio.
Well, that's actually a hard question, and I'm not an engineer, but in my dim understanding, if you have a transmission grid that is heavily loaded and you lose a critical segment, the electricity automatically flows into the rest of the grid. Within a second or three, you've triggered the cascading failure. And so if you want to prevent the cascade, you really have only two choices. You can either very quickly, within a second, generate a lot more power to feed the load that was on the other end of that transmission line, like the city that's consuming power. But you can't do that. You generally cannot bring up gigawatts of power transmission or power generation capability within seconds. It takes longer than that. So that doesn't work. The other possibility is to cut the load. You could say, I've got an emergency, drop the whole city, and now the grid is not going to cascade to other cities. It's possible to do that, but in my understanding, what was actually done after the 2003 failure was a lot of engineering, a lot of design, so that the grid is just never that stressed, so that you never even come close to a cascading failure. How do you do that? In my understanding, there was a new technology at the time, something called synchrophasers. These are devices that, in a sense, measure the stress on the grid and give you the grid operators early warning that problems are happening, so that 20 minutes beforehand they can say, start up that more expensive generator. I know it looks like we don't need it, but early warning says if we lose this chunk of the transmission grid, we're in deep trouble. I know it's more expensive. Start the generator anyway. So you need less of the transmission system. So that's synchrophasers. Or you could say, look, we got warning 10, 20 minutes in advance. We've got to drop some load so that we're not in this right on the edge of disaster condition. And you start giving orders to the city, to the biggest loads in the city, saying, drop your load for 2 hours. I'm exercising. And there's agreements you have with the large consumers saying, twice a year you can ask them to do this, something like this. And there's other things you can do sort of on the operations side. You can schedule maintenance on facilities to avoid, better avoid sort of high usage times, so that you have everything sort of up and going when you need it most urgently. So these are all engineering changes, and in a sense, and as far as I know, I'm not an engineer, but as far as I know, there was a lot of engineering done on the grid in response to the O3 outage, and it's sort of testament to that investment that it works, that there hasn't been another outage like that since '03, even though the grid has grown and become more complicated in the interim.
Did you know that power plants are exempt from 1/4 of NERC requirements when those plants use Waterfall's unidirectional security gateways? NERC does not demand that power plants use the gateways, but the regulations recognize the strength of unidirectional protections. The regulations reward sites who use gateways by dramatically reducing the number of security rules for those plants. For details on the exemptions, please download Waterfall's latest report on the NERC standards. You can find the report on the waterfall-security.com website in the Resources tab under eBooks and White Papers.
So we're coming to the topic of, in a sense, lessons learned from using the CCE process in a risk assessment. You've done this now. I haven't. I'm curious to know, what have you learned from the process, about the process, or, about security generally? What are the interesting takeaways here?
Well, I have identified many takeaways that can be used to help inform utility decision processes, regardless of what utility you belong to. And these decision processes can allow us to potentially reduce the risk of a high consequence event by just taking these things into consideration when making decisions. And I'm going to give you a couple of those. Standardization is one of those. Organizations use standardization to unquestionably increase efficiencies, and that's a good thing. But along with those discussions on standardization and really how you're going to implement them and roll them out, along with that needs to be an understanding that when you standardize, that is actually increasing the breadth of the attack surface. Because if you consider supply chain type attacks in particular, and I'm going to use some examples that really didn't come into our discussion processes, but like, for instance, if you had a standardized PLC vendor or a standardized COM vendor, you're actually, as you standardize, you're increasing the risk of an increased attack surface. And that can result in a high consequence event. So it's important to make, when you make those types of decisions, to understand that. And one of the good news things about standardization that we discovered is because often in the electric sector, and I think in a lot of control system sectors, you're dealing with old equipment and trying to standardize onto some new equipment, but the process takes a long time. Well, if the process is taking a decade, you're actually mitigating some of that high impact risk because you don't have as many facilities impacted by that example of a supply chain attack. And then one of the things that you may consider when you're rolling out a standardization initiative, you could decide to make sure that the standardization is happening in disparate areas, so that if the standardized vendor is attacked, but you still have some old equipment, you'd have enough of both in all the different areas so that your attack can't impact all your visibility and all your control. You would still have visibility from the remaining locations. And I know that's kind of a detailed answer, but that's a little bit about standardization. I also wanted to talk about consolidation, and this is absolutely a non-WAPA example, because I know industry is having a lot of mergers and acquisitions, and so you may have smaller control areas that are being consolidated into a larger organization, and they may want to consolidate operations and so on. And all of that is good, and it leads to efficiencies, but you could potentially be creating a single point of failure, and as Andrew Ginter taught me, a single point of compromise by doing that sort of thing. Doesn't mean you don't do it, but maybe you want to consider having some diversity. And when you bring in these SCADA systems from these other organizations, leave them intact and have, the guys on the desk that are operating the grid don't need to know whether they're operating on a different box, than the guy that's operating from the previous company on the other area. and I hope that makes sense, but that is really, a consideration. These are large business decisions that could have large consequences if you don't consider that you might be able to diversify your risk a bit and distribute your risk across multiple SCADA systems instead of a single.
This point about a single point of failure, it's something that we've discussed before on the show, but maybe not in a ton of detail.
That's right. Jodi's insight, she says, specifically here, standardization reduces the number of vendors involved, which means it increases your exposure to, the mundane defects that might be evident in a particular vendor's product. It increases exposure to vulnerabilities that might be embedded in a particular vendor's products. It increases exposure to attacks that might get deliberately embedded in that product by an adversary who's broken into the vendor. The sort of the strongest recent example of that was the SolarWinds Orion. So standardization increases efficiencies. It reduces the number of vendors. It reduces the amount of training we have to provide to the organization because there's just less stuff to train them on, but it has its risks. And, Jodi made the point as well, in a sense, single point of failure is another concept that is relevant to, she called consolidation. I think of it as centralization, where you acquire things and you sort of roll capabilities into a big, central, powerful control center. This control center, you're basically building it out bigger and bigger so it has more and more reach into the organization or into the grid. This makes things more efficient. You have, lower costs. You can build up specialties in terms of the people in the control center. There's benefits, cost, efficiency benefits to that kind of centralization, but it also increases the possibility that if somebody breaks into that control center, it increases the reach of the adversary as well as increasing the reach of the organization legitimately. And the phrase that Jodi used was single point of compromise. That phrase, in a sense, is an example of what the writing I did in the Black Book, the Secure Operations Technology book. I wrote that book by talking to experts like Jodi. I did talk to Jodi, as part of pulling ideas together for that book, giving those ideas names and feeding those ideas back to those same experts. And I'm very pleased to hear that, feedback from Jodi that she and, hopefully other people like her who are using these ideas, they think that process of gathering, consolidating, and feeding it back had value. So I'm delighted to hear this, the feedback there. So those are interesting examples, consolidation and standardization. You wouldn't normally think those would be, in a sense, contributing to threat. I'm pretty sure, when I read CCE, it didn't have in there words saying, hey, have you thought about standardization? That's not, in a sense, part of the process. Can you talk about how insights like this come out of a risk assessment process? How do you draw these conclusions?
Yeah, I'm glad you brought this up, because I want to be very clear that the CCE process isn't defining these particular scenarios. These are just something that are my takeaways after discussing severity. The CCE process walks you through establishing a scoring for severity for your organization or in general. And when you walk through that scoring process, you start to see what factors can lead to higher impacts. And so these are a couple of takeaways that I thought apply to all of industry as they make decisions around standardization and consolidation.
Was there anything else that you took away from the process, from this process of using CCE?
Yeah, there's actually a couple of really important takeaways that I haven't addressed yet. One of these is the length of reconstitution time. What I mean by that is when you're determining what severity, the higher level severity attacks, one of the determinants is how long is it going to take you to recover? And one of the things that this brought to mind is that a lot of the resilience strategies that you have within your normal operations to deal with day-to-day outages and so on could be beefed up to enable you to have greater control over how long it's going to take you to recover after an attack occurs. And so that was because what I learned from CCE is how significant that is in determining the level of consequence involved. So if organizations want to take that away, they could spend some more time determining whether they have the capacity to rebuild and recover from catastrophic events. And we're not talking just, I have a failover and a SCADA system that'll fail over. This is so much more. This is understanding whether or not you could possibly put out of band data validation capability in place and things like that enable you to quickly understand whether your system can be trusted.
And that makes sense. I mean, for the whole power grid. I mean, the power grid's critical infrastructure downtime is a bad thing. So that's a useful insight. You mentioned a couple of insights. You've given us one of them. What was the other one, please?
Oh, yes. I don't want to miss the opportunity to talk about the less recognized but highly valuable outcome of having these experts, this group of experts from the different professionals that are responsible for substations and substation maintenance and engineering, operations and operations engineering. Then you've got your SCADA folks that are tied in closely with operations, but they are definitely distinct and have a great responsibility with regard to the process. And then you've got IT folks that are enabling the IT infrastructure that the SCADA operates on. And finally, you got your cyber folks. So all of these disparate groups under the CCE engagement come together and review in great detail all of their dependencies. And the better we understand those dependencies and then their processes and their activities around maintaining equipment and so on, the better we can each be about understanding how our individual decisions in those different groups can result in higher impacts to the entire process. And underlying it all is just the understanding of that, what can happen in a cyber attack and how all of these processes interrelate in causing potentially causing that high consequence event. With respect to this CCE process, we ultimately, by bringing those folks together, I believe we've improved greatly and helped bridge the IT-OT divide that everyone has struggles with. So it's kind of a side benefit, but it's very valuable. And that is one of the things CCE does is allow that group to get together and understand the dependencies amongst each other and get used to working together. I mean, if we were attacked, I think that's the same group that's going to get called on to address how to rebuild.
So it's been long enough that this has sort of become a theme on our podcast, bringing everybody together. The IT people, the OT people who sort of see things differently, the engineers who have an entirely different skill set.
Absolutely. This is sort of a common theme. I mean, think about CCE. In a sense, it's all in the name. Consequence driven. So there's been a lot of focus on consequences here. And to understand the consequences, you need engineers in the room. You need the safety engineers. We need the equipment protection engineers. We need the process engineers. Consequence driven, cyber informed. So we need the cyber people in the room too. We need the people who understand how the control system, the automation is put together. We need the infrastructure people from IT to understand how the control system relates to the overall infrastructure. We need we need the penetration testers, the people who understand attacks, to look at the infrastructure and point out where attacks might come in. So consequence driven, cyber informed engineering. In the end, a lot of what's happening here is engineering, redesigning the system so that it's less vulnerable, not necessarily increasing the strength of the passwords so that it's less vulnerable, just changing the design of the system so the vulnerabilities don't exist. So, this is the nature of CCE, and it's nice to see it in action here. Looking back over, the interview here, the answers that you've given me, thank you for that. I haven't heard you use the word security very much. I mean, you've talked about time to recover. That sounds like a resilience thing. Can you talk about is that deliberate? Are we talking about resilience more than security?
Well, that's a great question, and one of the things to understand about CCE is that the focus on consequences and so on is going to make this more of a process of working with the professionals that deal with resiliency. Honestly, it's the ones that are making sure that the operations continues. It's the ones that make sure that the substations are operational. Those are the folks that are the most able to determine consequences. And so the security professionals, for the most part, at least in the earliest stages of the CCE engagement, they're really just listening and learning. They're learning about the dependencies and processes. At later stages of the CCE process, they may be able to identify some protections, but earlier, if you don't find ways to mitigate the risk through processes that the maintenance and operations engineers and SCADA engineers identify that could actually avoid the consequence to begin with. So the cyber professionals kind of play a different role in this CCE engagement. They are more there to help us understand the types of attacks, and because there's always an assumption in CCE that you are attacked and you couldn't thwart it, but you are attacked. Well, that takes away all of their input regarding how they're going to stop the attacker, because it's just given in a CCE engagement that you're going to assume that the attack is going to happen.
Jodi, it's been great catching up with you. Thank you for joining us. Before we let you go, can you sum up for us? What is it that you'd really like our listeners to take away from this episode?
Well, I really hope that folks understand that cyber protections are only one part of the diligence that's needed to protect the assets from a cyber attack. consider within your own organization, do you have isolation strategies in place to reduce the consequence of a ransomware attack? Do you have reconstitution processes that allow you to quickly regain and understand whether the data is trustworthy? Do you have a decision-making process when you're making decisions about changes to your architecture or changes to your technology? Have you incorporated considerations around whether you're increasing the severity of a potential attack? Things like attack breadth. Are you expanding the breadth of what an attacker can accomplish by the decision you're making? And these decisions go all the way to the top. One thing about CCE, they gave us visibility of all this is being given to the senior leadership. We took our CCE information to them so that they understand what the types of catastrophic scenarios are that we're playing out, and they get to have feedback and input into which ones need the most effort around mitigation and resilience. And so think about whether your organization has awareness of the consequences, high consequence events, and whether that goes into decision processes. If you think that more is needed by your organization, I would recommend working with the experts at INL who are doing CCE engagements, but they've also enlisted the help of the private sector in getting involved in CCE as well. And so those folks could help you, and I would be glad to work with you as well. I would bring that boots on the ground background in implementing secure solutions to any type of work that you need done. And so consider contacting me at Jodi Jensen at securescadasolutions.com.
Andrew, could you take us out with something?
Sure. I mean, what stuck with me in Jodi's discussion of the whole process, there's what's the right word? There's in a sense debate in the industry. There's voices in the industry that are sort of focused on one thing at a time. There's voices who are saying, look, nothing is ever cyber secure. There's no such thing. You can't be secure. And so you must assume that sooner or later you're going to be compromised. And so it's vital that you have the ability to detect, respond, and recover, regarding those compromises. That's sort of the cyber perspective of the situation. There's the other end of the spectrum is the engineering spectrum that says, look, nothing is secure. And so, we have to, wherever possible, wherever practical, engineer attacks entirely out of the system. Engineer the system to keep working, maybe at a reduced capacity, even if it's under attack. It may be not as efficiently as before, but it does keep working. So, there's these voices talking about detect, respond, and recover versus engineer the system, to be more robust. Both of them are needed here. CCE focuses on the engineering end of it, but both sets of perspectives are valid, and it's nice to see the engineering perspective being developed here, because it really hasn't been emphasized very much in the first 10 years of the discipline.
Right. So thanks to Jodi Jensen for that. And as always, Andrew, thank you for speaking with me.
Always a pleasure. Thank you, Nate.
This has been the Industrial Security Podcast from Waterfall. Thanks to everybody out there listening.